Okay, I will start. Hello, Kavita and Lakshmi Reddy.
Good afternoon, sir.
Good afternoon. Good afternoon. Okay.
Good afternoon.
Okay. Good afternoon. I will share screen. Share screen is. Okay. Today topic is. This is epsilon net neighborhood. Yesterday I will also discussion epsilon net neighborhood. Also.
Sir, please tell me the page number, sir.
Page number వచ్చేసి this is page number 44. 44
or 34, sir?
44 4,4.
Yeah.
Totally bounded set. Totally bounded set.
Okay.
Set, see that totally bounded set. Okay. So the totally bounded set we count to definition. I am to page number that theorem statement. I am to already notes prepare. I will to send the notes. I will prepare notes are there. Okay na?
Sir, ఎలా సెండ్ చేస్తారు సార్ నోట్స్ అనేది?
నేను ఆల్రెడీ సెండ్ చేశాను మీకు రియల్ అనాలిసిస్ గ్రూప్ లో పీడిఎఫ్ నోట్స్ సెండ్ చేశాను. ఇప్పుడు నేను స్క్రీన్ మీద మీకు ఇప్పుడు నోట్స్ అవపడుతుంది అనుకుంటా.
అంటే సార్ అది కాదు సార్, మాది రాజమండ్రి సెంటర్ సార్.
ఓకే.
సో అలా అవ్వదు కదా సార్ మరి.
ఓకే, రాజమండ్రి సెంటర్ అంటే మీరు అట్లా ఉన్న నెంబర్ నా నెంబర్ రాసుకొని నాకు వాట్సాప్ చేయండి. హాయ్ అని పెట్టండి, నేను పంపిస్తాను.
చెప్పండి సార్.
9949
9949
060
060
102.
10. ఓకే.
అంటే అవుట్ ఆఫ్ మీరు ఎవరు ఉన్నాం మీ ఫ్రెండ్స్ ఒకరు గ్యాదర్ చేసుకోండి, నాకు ఐ విల్ సెండ్. ఓకేనా?
ఓకే సార్. ఓకే సార్.
రైట్. నౌ ఇన్ టోటల్లీ బౌండెడ్ 4.5 sets లో we have the definition is epsilon net. So what is the definition is epsilon net and totally boundedness. Epsilon net and totally bounded set అయితే what happened is the definition is called is. The definition is, so it is called is, so definition is x comma d is a metric space. What is now? Now tell, x comma d is a metric space. X is a metric space. So the given x is a metric space, given epsilon greater than 0, x comma d metric space. So given epsilon greater than 0, capital A subset of capital A subset of x, a set B, again two sets are there, a set B, A set B set are both are a points of x, be a points of x is set to be epsilon net, is set to be epsilon net, is set to be epsilon net. So for A, if for each x belongs to A, we can sum y belongs to B. And such that distance of x comma y is less than epsilon. Distance of x comma y is less than epsilon. Naturally what happened? X comma d are metric space. A comma b are two sets of capital X subsets of x. So is set to be and a set to B of points. This is the points of x is set to be epsilon net. So what is now distance of d of x comma y is less than epsilon. For some y belongs, like what happened is d of x comma y is less than epsilon. X is belongs to A, y is belongs to B. So x is a point of A, y is a point of A. So we are testing to the definition for a metric space. Okay. All of you. Okay, this is. Okay, now this. Yes, all of you. So epsilon net definition is one type. d of x comma y is less than epsilon. Same definition your textbook is. A metric space x comma d, a metric space x comma d is said to be totally bounded. For given epsilon greater than 0, we can find a finite epsilon. Is said to be totally bounded. A given epsilon, we can find a finite epsilon net. Finite epsilon net. And we can find a finite set points. So what is the finite set points? X1, x2, xn, the points of. So the union of that is S of xi comma epsilon. So I is equal to 1. Is a totally bounded is clearly x is a bounded. And indirectly S epsilon of xi. This is S epsilon of xi is called is open sphere. S epsilon of xi is a open sphere. It's called also is a points is called is a totally bounded set. X is a totally bounded, then X is also bounded. Actually, your textbook is a epsilon net is a definition is called this. A finite set given epsilon net is equal is a union of. So this is called this. A point epsilon x be a metric space, a finite subset of E of x in such that capital X is equal to union of small a belongs to capital A, S epsilon of A. S epsilon of A, that is also epsilon. A is called is epsilon net. Every epsilon net, a metric space X is said to be totally bounded. It has an epsilon net. X is a metric space. What is a union of small a belongs to capital A? S epsilon of A, it is also epsilon net on top. A set has epsilon net. The set has epsilon net. It is called is totally bounded. Totally bounded. So this is totally bounded. Totally bounded, I think it is a clearly X is also bounded. A metric space X is said to be totally bounded. Epsilon net for each epsilon greater than 0. It has epsilon net. So what is the epsilon net? S epsilon of a open sphere. Union of a open spheres. Union of a open sphere is means S epsilon of point of A1 union, S epsilon of point of A2 union, S epsilon of point of A3 union up to so on. S epsilon point of AN. So all of them can be written as union of small a belongs to capital A. S epsilon of A is equal to total metric space. I think that is called is epsilon net. Any metric space it has epsilon net, that is called is totally bounded. So totally bounded. So we learn. So this is the first page we can do definition. Epsilon net and totally bounded set definition. So your note, this is the second page. So it's a clearly, this is the second page is. So what is the second page is called is? X is a totally bounded set is also bounded. A is an epsilon net. So what is X is a totally bounded, this is a totally bounded. X is a totally bounded, X is also clearly bounded. Suppose capital A is a set is an epsilon net. Small x comma y is belongs to capital X. There exists A comma B belongs to A such that X is belongs to S epsilon of A, Y is belongs to S epsilon of B. So S epsilon of B. So this is a meaning of Kachurandi. X is belongs to S epsilon of A and meaning into the that is the D of X comma A is less than epsilon. Y is less than X epsilon of B and meaning what is the meaning? D of Y of B is less than epsilon. That is called is a open sphere. Is nothing but open sphere. I am taking this is called is an open sphere. So these are open spheres. D of X comma Y. D of X comma Y is less than or equal D of X comma A plus D of A comma B plus D of what is the D of B comma Y? Triangular property. D of X comma Y less than epsilon plus D of A comma B same is a plus D of B comma Y is a epsilon. Epsilon plus epsilon into epsilon plus D of A comma B. So D of A comma B. So this is 2 epsilon is equal to, and D of X comma Y is equal less than or equal to 2 epsilon plus delta. And it is a D of A, diameter of A. This is a, it is also epsilon point is now. It's a clearly this is a discussion is now this is second note. Y is a metric space. Y is a metric space. Y is a metric space. X is subset of Y. And X and Y are both are metric space. But X is totally bounded. Totally bounded. I think then X bar is also totally bounded. Totally bounded. Then X bar is also totally bounded. Okay. X is a set of Y. So X is a totally bounded. And X is a totally bounded. Then X bar is also totally bounded. So what is the discussion is? Small x belongs to X bar. There exists a sequence. A sequence is Xn. In X is convergent to. So a sequence is converges to X. What is the definition convergent? Given epsilon greater than 0, we can find. So we can find a natural number n such that so small r n is greater than or equal to n. So we can do this is a process. So it's called as small x is belongs to X bar. X bar is total bond. There exists a sequence. Xn is a sequence. Xn is a sequence. Is converges to X. What is the definition? Epsilon greater than 0. We can find a natural number n greater than or equal to n. So what is the d of xn comma x? D of xn comma x less than epsilon by 2. D of x comma xn is also less than epsilon by 2. So next ikkada d of inken chuskochu x comma capital Xn is also is less than epsilon by 2. Is less than epsilon by 2. It's called this d of. So we can do if A is an epsilon, if A is an epsilon by 2 net, A is epsilon by 2 net in X, epsilon net or epsilon by 2 net X. What is the definition? D of Xn. This is the D of Xn comma A is epsilon by 2. Epsilon by 2. D of Xn comma A is epsilon by 2 for some small a belongs to A. This is clearly d of x comma a, d of x comma a is less than or equal to d of x comma xn plus d of xn comma small a. What is that? D of xn comma xn is the less than epsilon by 2 plus epsilon by 2 is equal to epsilon by 2 is epsilon. So what is now? D of x comma a is less than epsilon. D of x comma less than a, x is belongs to S epsilon of A, open sphere. X is belongs to open for some small a belongs to A. So for some small, so A is an epsilon net. A is, this is a definition is called A is epsilon net. A is an epsilon net for X bar, for X bar. Hence, A is epsilon. A set having at least one epsilon, that is called as totally bounded. So Koti, what is now? This is the meaning. D of x comma a is less than epsilon. This is x is belongs to S in epsilon of a. So for some small a belongs to capital A. So x has epsilon net epsilon. X has an epsilon net today. X bar is epsilon net. Then x bar is totally bounded. Totally bounded. So this is a totally bounded. So this is the second page is also completed. Now the second page is complete. Now this is the next one paper is completed. Next we are go to the theorem. So what is the theorem? In textbook in page number theorem 4.5.3, that is the theorem is page number 45. 45 page number theorem is. So what is the theorem is? The statement is called is. So tell me, this is the page number 4. Now, okay. A sequentially compact metric space, is it totally bounded? A sequentially compact metric space, is it totally bounded? A sequentially compact metric space is totally bounded. This is the theorem 4.5.3. A sequentially compact metric space is totally bounded. Yes. Okay. Now, once again, all of you, 4.5.3, a sequentially compact metric space is a totally bounded. So, a totally bounded. Okay. A sequentially compact metric space is a totally bounded. Yes, is listen to me. First one, sequentially compact metric space. What is the sequentially compact metric space? So first one, this is X comma D metric space. Sequentially compact metric space. What is the sequentially compact metric space? It has a finite subcollections. A compact matrix. Compact call it a finite subcover. It is a family of a open subcover. It's called sequentially compact metric space. So X comma D be a sequentially compact metric space. Let epsilon greater than 0 given. X1b is a one arbitrary point. Okay, now. So X comma D, this is X comma D is a sequentially metric space. So be a sequentially metric space, compact metric space, epsilon greater than 0. X1b arbitrary point in X1b point of X. So X1 belongs to X. If a method this is, so if is S epsilon of X1 is equal to capital X. S epsilon of capital X1 is equal to the sequentially metric space. Or then it would write S of X1 comma epsilon is equal to capital X. A sequentially X1 is belongs to capital X. Capital X is a sequentially compact metric space. A definition is must be a open sphere S epsilon of X1 is equal to capital X. X1 is equal to capital X. So the singleton X1 is an epsilon net, and the theorem is proved. And it is called is totally bounded set is called is a set having at least one epsilon naught. And it is X singleton X1 epsilon naught, but it is a epsilon naught. It is a X is a totally bounded. The theorem is true. The theorem is singleton X1 is the theorem is proved. However, and it's not epsilon naught. And however, there exists this is called is. However, there exists a second point. However, there exists is second point. X2 belongs to capital X, such that X2 does not belongs to the open sphere X epsilon of X1. Okay, and S epsilon of X1 use a union of S epsilon of X2 is equal to capital X. That is called is X1 X2 points. To union of a open sphere is equal to capital X. The capital X is called is sequentially compact metric space. Sequentially, then so this is a then set X1 comma X2. Then set is X1 comma X2. Then X1 comma X2. Then X1 comma X2 is epsilon net. Then X1 before is singleton X1 is epsilon net. What is the now? The set X1 X2 is epsilon net. There is the theorem is proved. At least epsilon net is called as totally bounded. Is listen to me. X2 is belongs to capital X. X2 does not belongs to the open sphere of X2, such that and so S epsilon of X1 is a union S epsilon of X2 is equal to capital X. So that is the set is X1 comma X2 is epsilon net. A set having epsilon net, the set is X is totally bounded. Totally bounded. Totally bounded. And singleton 1 is a totally bounded. Singleton x1 comma x2 is a totally bounded. Next time, x3 is a belongs to capital X, and such that x3 is a does not belongs to S epsilon of x3. And em diskunta S epsilon of x1 union S epsilon of x2 union S epsilon of x3 union is equal to capital X. X is a sequential compact metric space. The set is x1 comma x2 comma x3. Set is epsilon net. A set is at least one epsilon naught epsilon net, that is called as this totally bounded set. So this to continue the process, the epsilon naught in the continuing the process is S epsilon of x1 union S epsilon of x2 is a union up to so on union S epsilon of xn. S epsilon of xn is equal to capital X, is equal to capital X. We note the process, we note that process, a terminate after n steps, a terminate after n steps, because some process of could not continue indefinitely, the sequence xn, and the sequence xn, it has, so a containing, a sequence xn containing no convergent subsequence, no convergent subsequence, no convergent subsequence. It has no convergent subsequence. So this is which has a no convergent. This is a contradiction by hypothesis. What is the hypothesis? Sequentially compact. Sequential compact undalante a sequence xn, it has a convergent subsequence, that is called as a sequential compact. This is a contradiction to hypothesis. What is the hypothesis? So a sequentially compact, it has a sequence, it is must be. So it is a must be. It's called is a must be a convergent subsequence. After the terms, what happened is, we know that process sometimes it terminates after n steps because of some process could not continue to identifiedly. Then the sequence xn in X would be a sequence containing no convergent subsequence. This is the contradiction. Hypothesis X is a sequentially compact. It follows that. So this is, it is follows that. So this is, it follows that. This is the page. So it is follows that. It follows that. It follows that x1, x2, xn. So this is a follows that x1 comma x2 comma xn. So it is a follows that x1, x2, xn is an epsilon net. So therefore epsilon net, and hence X is totally bounded. X is totally bounded. X is a totally bounded. The theorem is completed. So X is a totally bounded. The theorem is completed. Next to 4.5.4 theorem. So what is the 4.5.4 theorem is? Every sequentially compact metric space is compact. Your textbooks low 4.5.4 theorem is bounded, but bounded is wrong. Every sequentially compact metric space is compact. Akada is a total sentence is wrong. Your textbook is 4.5.4 theorem low totally bounded sentence is wrong. Print mistake. So that is must be compact. So what is the theorem 4.4? So the every sequentially compact metric space is compact. So is compact. So this is called is the theorem is. Now let x comma d is a sequentially compact metric space. Let x comma d is a sequentially compact. What is now x comma d? Be a sequentially compact metric space. Sequential compact metric space. A sequence x and x, it has a convergent subsequence. Is called is a sequential compact metric space. So it is a, now I am taken C is equal to the set of G alpha such that alpha belongs to high. So alpha belongs to high is a behind open cover of X. Behind open cover of X. Behind arbitrarily open cover of X or behind an open cover of X. Open cover of X and open cover of X. Behind open cover of X. So since X is a sequentially compact matrix space, ikkada open cover of X, since X is a sequentially compact matrix space in previous theorem 4.3.7, C is equal to, so G alpha such that alpha belongs to high, has a Lebesgue measure, a Lebesgue number, a Lebesgue number, Lebesgue, SG, a Lebesgue number, a Lebesgue number. A Lebesgue number ఏమనుకుంటున్నా small a is greater than 0. A Lebesgue number is small a greater than 0. What is the definition is epsilon is equal to a by 3. It is a greater than 0. Equation 1. So since x comma d is a sequentially metric compact metric space, so what is a compact metric space? I think it is a previous theorem. It is totally bounded. It is totally bounded. So totally bounded, hence it has sequence total boundality. It has epsilon net. What is the epsilon net say? So that is epsilon is equal to a by 3 greater than 0. So X is a sequentially compact metric space. This is the previous theorem is a totally bounded. The totally bounded is called is, say, epsilon net is. What is the total bounded epsilon net is? Small a1, small a2, up to so on small n. Then X is equal to totally bounded formula union of, so open sphere S epsilon of xk such that k is equal to 1 to up to so on n. K is equal to 1 to up to so on. This is equation number 2. So I'm taking equation number 2. So this is a clear. So epsilon is our equation number 2. So I have to write here. So this is d of s epsilon half. So it is called this d of s epsilon half. D of s epsilon half. What is now? D of s epsilon of xk such that k is equal to 1 to up to so on n. Equation. So up to what is the d of s epsilon of xk? So bracket is less than or equal to 2 epsilon. So is equal to 2 epsilon is a value a by 3 to 2a by 3. 2a by 3. So this is d of s epsilon of xk. Okay, this is less than 2a by 3. 2a by 3 always less than a, is less than a. For all k is equal to 1 to up to son n. So 1 to up to son using 1. So using 1. So same thing by using 1. So using 1 now. For each k is equal to, so for each k is equal to, so this is for each k is equal to 1 to up to so on n, a delta half s epsilon of xk, okay, is less than a, and hence by definition Lebesgue number, there exists at least one g alpha of k such that s epsilon of xk is a subset or equal to g alpha of k. Where is the k is equal to 1 to up to so on. 1 to up to so on. We have to both side apply union. So we have to both side apply union. In this s epsilon of alpha of x, sorry, s epsilon of xk such that k is equal to 1 to up to son. One set left hand side. So is a g in subset or equal to g of alpha of k. Both side apply union. Union of the set s epsilon of xk such that k is equal to 1 to n. This is a subset or equal to union of g alpha k in k is equal to 1 to n. Using second, x is subset or equal to union of g alpha k. So what is now? X is subset or equal to union of x is subset or equal to union of g alpha k. So that k is equal to 1 to n. So 1 to n using 2. So is a finite subcurve. Is a finite subcover. This is called is now. Is a finite subcover. So this is called is a finite subcover. Now it is called is a x is a x is subset of union of g alpha k. K is equal to 1 to n using 2. So this is a C is equal to G alpha K such that K is equal to 1 is a finite subcover of C. C ikkada raipina. So only set the set G alpha K such that K is a belongs to 1 to N. Okay, K is a belongs to 1 to N is a finite subcover of C. Hence, X comma D is a compact. What is a compact is called is a set is said to be a metric space is said to be compact if it has a finite subcover. X comma D is a finite subcover, then is called as compact. A sequentially compact metric space. Sequentially compact metric space is compact. Okay, this is a theorem is close. Next is called is in 4.5 theorem. So in page number 4.5.5. So this theorem you can using the already we learned to this. You are R equivalent to. So the metric space X is following the three properties are equivalent. The properties are equivalent. So what three properties are equivalent. Three properties are equivalent. So X is compact, X is sequentially compact. So X is a satisfy the Bolzano-Weierstrass property. Now, this is X is a compact, X is a sequentially compact, S is satisfied Bolzano-Weierstrass property. So, man em chale 3 steps. A implies to B, B implies to C, C implies to A. Automatically, all are equivalent. All are equivalent. So, ikkada already man theorem proof 4.3.13. So, the proof is theorem is 4.3. So that is a theorem proof is okay. The theorem proof is so 4.3.13 theorem copy cheyale A implies to C. Next by theorem 4.3.14 theorem cheppanu if and only if C if and only if B. Hey, C if and only if B వచ్చిందంటే ఏంటిది మీనింగ్ నెక్స్ట్ 4.5.4 only B implies to A. So B if and only if అంటే C implies to A. C implies to A implies to A అంటే C is equal to A. అంటే A implies to C, B is equal to A. A if C, B is equal to C and both are equal. B implies to A. What is the B value equal to C? అంటే C implies to A. A implies to T అంటే C is equal to AC. అయిపోయింది అంటే all are A implies to C, C implies to double implies to B, B implies to A. And A implies to B, B implies to C. So we have to copy. It's not examination, same not given. It's not given in the examination copy. This is not given at least to 0 marks. But I am to write here. This is a copy. The theorems we have to already completed. The theorem copy will be there. A implies to C, 4.3.15. A if and only if B, 4.3.14. So B implies to A, 4.5.4. Totally the theorems will be copied. One A implies to B, B implies to C, C implies to A. The theorem is completed. Already discussion is the total theorems is completed. We can copy this, the notes, my notes yesterday, send the PDF notes yesterday. I have to the same theorems also. So next is. So this is called is 4.5.6. So this is a 4.5.6 next theorem. What is a 4.5.6 is? So it is a metric space X is compact if and only if X is complete and totally bounded. X is complete and totally bounded. This is called is. (4.5.6). So X is a metric space. A metric space X is compact if and only if X is compact, and a metric space X is compact only. I think this is if and only if X is complete and totally bounded. What is the complete is? X is a metric space complete column. If it has a Cauchy sequence is a convergent sequence is called complete. Totally bounded column. What is the total bounded? A metric space is said to be total bounded. It has epsilon net. What is the epsilon net? The open sphere is equal to the union of a open sphere is equal to a given metric space, that is called is epsilon net. A set to a metric space is set, it has epsilon net, that is called is a totally bounded. X is complete column. Every Cauchy sequence is a convergent sequence. That metric space is called is complete. Every Cauchy sequence is a convergent sequence is called a complete. So ham to theorem proof chudandi. So then by theorem X comma D is a sequentially compact metric space. X comma D is a sequentially compact. So by theorem 4.5.3 theorem previous, it has totally bounded. Sequentially compact, it has totally bounded. It is X is totally bounded. X is a totally bounded. Now we prove that X is complete. So totally bounded completed. Only complete and neutral. Complete neutral, since every sequence in X, it has convergent subsequence. A Cauchy sequence Xn, a Cauchy sequence Xn in X must have convergent sequence, and therefore it must itself convergence. X is complete. So Cauchy, it is a X totally bounded. X totally bounded approve. X comma D is a sequential compact metric space. In previous theorem 4.5.3 copy chala, it has totally bounded. Total bounded completed. We have to prove X is complete quality. It has a convergent sequence. Every sequence in X, it has a convergent subsequence. A Cauchy sequence Xn. A Cauchy sequence Xn is X must have a convergent subsequence. The convergent sequence. So therefore it must itself is convergence. So hence X is complete. So it is called is next is conversely part. What is the conversely part is called is? So this is a conversely part. So the conversely part is, let X be a complete and totally bounded. X be a complete and totally bounded. So we shall prove that every sequence is a Cauchy sequence. Every sequence it has a convergent Cauchy sequence. It is called as complete. So complete differential. We shall prove that every sequence has a Cauchy sequence. X is complete. That is means that every sequence has a convergent subsequence. X is a totally bounded. Xn is a Cauchy subsequence in say X. Cauchy Xn. So this is Xn, a sequence. It has a subsequences Xnk. It is a subsequence Xnk. It is also a Xnk. A subsequence is Xnk. Now, a subsequence Xnk. Now, Xnk. So therefore, is Xb is complete. Xnk and Xb completed. Xnk must be a convergence, and therefore X is a sequentially compact. Every sequence Xn is a convergent subsequence is called as a sequentially compact metric space. Sequentially compact. Okay. So this is called is once again now. Now, 4.5.16. A metric space X is a compact if and only if X is a complete and totally bounded. X is complete and totally bounded. So this is called. In a sequentially, this is. Okay. Now, X comma D is a sequentially compact metric space. X comma D is a sequential compact metric space. In previous theorem, it is totally bounded. It is a totally bounded. So totally bounded completed. Next, we prove that X is complete. Complete definition. What is a complete? The complete ante it has a sequence Xn. A sequence Xn is a Cauchy sequence, a convergent Cauchy sequence. A sequence Xn is a convergent Cauchy sequence. It is called as a Cauchy sequence Xn in X must be convergent sequence. It is called as complete. So every sequence Xn has a convergent subsequence. And since X is a sequential compact, what is the sequential compact definition? A sequence X is a metric space is said to be sequentially compact. It has convergent subsequence. Already a sequence Xn, it has a convergent. This is a sequence Xn in X. It has a convergent subsequence. A convergent subsequence. A Cauchy sequence is a convergent that is called is complete. So it's called is complete. So this is called is itself complete. Conversely part. X is complete and totally bounded. We prove that X is a sequential compact. We shall prove that every sequence Xn is a Cauchy sequence. It is called is X is complete. Then it must by every sequence it has a convergent sequence. X is a totally bounded. Xn is a Cauchy sequence. Xn is a Cauchy sequence. Xn is a Cauchy subsequence. Xn ko Cauchy subsequence untadi, that is Xnk is convergent. So X being a convergent, a Cauchy sequence X be complete. So therefore, Xnk must be convergent, and therefore X is a sequence Xn is a convergent subsequence. That metric space is called is sequentially compact metric space. Sequentially compact metric space. Sequentially. Nana sound takku. So essentially compact metric space. Okay. Now this is a close. Next is a topic is important. This topic is a connector set. What is a connector set is? This is a topic is. Now, a connector set is. Connector set kante before your topic is learning is separated sets. Separated, SEPERATED, separated set. Separated set is called as a definition. Suppose X is a metric space. Suppose X is a metric space. Two subsets A comma B, two subsets of X are said to be separated if A intersection B complement is equal to pi. A complement intersection B is equal to pi. Complement is or some closed also. A intersection B complement is equal to pi. A complement intersection B is equal to pi. A comma B are two separated sets. complemented is means B bar. Bar is means closed set. The set of all limit points is called closed set. It is denoted by A bar. And suppose X is a metric space. The set of all limit points is called as a derived set. The set of all derived set is called as a closed set. The closed set ante X is a metric space D of S in subset of X aithe, that X is called as the closed set. It is denoted by X bar. What is the D of S? Derived set. Derived set emuntadi? The set of all limit points. The set of all. What is the limit points? We got a neighborhood. So it is a point is set to be neighborhood. It is a infinite number of points. So the set of D of S. So a closed set. A closed set is denoted by A bar. X be a metric space. A comma B two subsets of capital X is said to be separated set. If A intersection B complement is equal to pi, or A complement intersection B is equal to pi. The complement A complement is called is a closed set. It's called as this is the meaning. We have to note also. This is note. If A and B are separated sets, then A and B are designs. A and B separated sets at A and B are designs. So A comma B are separated. And what is the definition? A intersection B complement is equal to pi. But every intersection A intersection B subset of A intersection B complement. A intersection B complement is equal to the subset of pi. And indirectly A intersection B is equal to pi. A intersection B is equal to pi at the sets is two different sets, a design sets. Different. There is no common elements. Design sets your meaning is called is A. It is a two sets. This is the design intersection. This is called is intersection part. So this is the intersection. It is called is A intersection B is equal to something. It is a empty. And what is a empty? That is a empty. That is, so it is A intersection B empty. This place is called is A intersection B is equal to empty. A and B are both different sets or different sets. So A comma B are separated sets, then A and B are designs. A and B are separated set, A and B are designs. The converse is not true. A comma B are separated sets, then A comma B are designed. Are designed. So A comma B are designed, then A comma B need not be separated set. Is it A and B are designed? Is the converse is true? No. So we have the topic is converse is, so that example is taken. So what is the example is taken is, so it's a clear now. No. So what now is A and B are design set need not be separated. So what is the A is equal to a closed set 0, 3. B is equal to open interval 3, 7. A intersection B is equal to empty designs. A and B are designs. A intersection B is a design. A intersection B complement. So A intersection ante 0, 3 closed set. A open set ko closed set it's a closed set. Intersection 3, 7. So 3, 7, what is the common element? Singleton 3 common. It is not equal to pi. A intersection B bar is not equal to pi. A and B are not separated. What is the separated? A intersection B complement is equal to pi is separated. Not equal to pi. A comma B are not separated. Not separated. Yes, yes. Hello, all of you. All of you meet now. Okay, this is a next. We have to notice. I am to clear not separated and Japan. So A and B are separated sets. No point of A. A and B are separated. No point of A is no point of A. is a limit point of B. No point of B is a limit point of A. And what is the meaning is A intersection B complement is equal to empty. Because it is no point of A, so it is a limit point of B. A complement intersection B is equal to pi. No point of B, it has a limit point of A. What is now A bar is equal to, this is a A bar is, that is D of A subset of A. I think then A is called as A bar. So A bar hitla kuda cheppochu. That is A bar is equal A union A prime. A prime ante the set of all limit points. So D of S. Itla kuda cheppochu. A union D of A. Derived set of A is equal to A union derived set of A. It is also A bar. So the derived set is the set of all limit points. Scott, it is clearly. So it is a clearly. Next is original. We can do learn. The definition is a connected set. What is a connected set is important. X is a metric space. E subset of X. X metric space. E subset of capital X is said to be connected. Is said to be connected if it is not the union of, so union of, it is the not union of two non-empty sets, union of two non-empty separated sets. So not union ante what is the A is not union of, E is equal to not a union of separated set. A and B are separated. So that is said to be E subset of X is said to be connected if it is not union of two non-empty separated sets. That is E subset are equal to X. E subset are equal to X. E subset are equal to X. E subset are said to be disconnected. Is a disconnected. E subset are equal to X is a disconnected. Disconnected and it's not connected. Not connected is meaning A and B are two non-empty sets. And the E is the union of A. Can be written as the union of two separated sets. A union of B can be written as union of separated set. That is called as a disconnected set. And E is equal to a union of two separated set. Then he is called as not a connected set. Not connected set his meaning is can be written as union of. Okay, not again. So what is the definition is very important. E is a connected set call and it is not equal to can be written as A comma B union of E cannot be written as the union of two separated sets. Suppose it's not it is a separate set. If it is not a connected call, it should be E is equal to A union B. That is the meaning. A intersection B is equal to a complement. A complement intersection B is equal to complement. And that is the meaning. A comma B are two separated sets. A comma B two separated sets, that is must be E is not a connected. Not a connected, other name is E is not disconnected. So if it is connected, A is not equal to A in B. E is a subset of a metric space X. E cannot be written as a union of two separated sets. Okay? That is called is a connector, is a connected set. This is a connected set. So that is a connected set. Okay. So this is the 4 pages, 4 papers is completed. So that's all. So or your textbook definition also. So this is a textbook is a definition is or now in textbook is a definition is a set E is a metric space X is said to be connected if there do not exist a two non-empty open subsets of A and B of X such that A intersection A intersection E not equal to empty, B intersection E not equal to empty, E both of them therefore E subset of A and B. So E's can be written as a E is a subset of A union B, that is called also a connected set. E is a metric space. E is a subset of metric space is said to be connected if do not exist two non-empty open subsets A and B. So open, ఇక్కడ complement ఇయ్యాలి A and open sets. So this is not. Then complement వస్తే it is a empty. So A intersection E is equal to empty అన్న meaning. So A intersection E is not equal to అప్పుడు A is this is a open. ఇక్కడ A bar is a closed set. That is called a closed set. Open, closed, that's the meaning. So next to 4.73 theorem. So this is important. 4.73. No. 4.73. The 4.73 theorem is, so we got కాలే తింటలేడా క్లాస్ చెప్తుంటే పొద్దున్న క్యాములు ఎక్కించినా ఒక్కసారి పొద్దున్న నుంచి ఫోను అన్నం తినమంటే Now theorem is X be a metric space, E be a connected subset of X, E be a connected 4.7.3. Okay, now this is a in page number 4.7.3, page number is 48 page number. Now in 48 page number, page number. So we write this is theorem is X be a metric space, E is a connected subset of X, E subset of X such that E subset of C subset of E bar, then C is a connected. In particular, E bar also connected. It's simple. What is of both of them? This is E and C are. ఇక్కడ E, C are both subsets of X. What is the X is? Metric space. What is a metric space? So this relation we can do. E subset of C subset of E bar. Then so C is a connected. Then E bar also connected in particular. So we given that. So what is the given that? E subset of C subset of E bar, equation 1. We have to show that. This is, we have to show that C is connected. We have to show that C is connected. So C is connected. I am to wrong sentence if it possible. So we have to show that C is connected. So I am to possible if it wrong sentence. If possible, wrong sentence is means C is not connected. Not connected is meaning disconnected. Disconnected definition is called. So the disconnected can be written as a non-empty sets A and B. C is equal to the union of can be written. The union of can be written as A and B are. C is equal to the union of the union of can be union of two separated sets. So two separated sets. The union of can be written as union of two separated sets. So what is the separated set definition? E is equal to can be written as union of two separated sets. Got it? So C is a cannot be written as union of two separated sets. Not connected, but is a union of. Therefore, two non-empty sets A and B, two non-empty sets there exist. C is equal to A union B. So we have the relation. A intersection B complement is equal to pi. So this is called this. So next time, C is not connected. Not connected is meaning C is equal to A union B. A comma B are separated set. What is the separated set definition? A intersection B is equal to empty. A complement intersection B is equal to empty. This is a relation. So it is called as the second equation. Already first equation, E subset of C subset of is he bar is called is the first equation. C, okay, C is a connected ankunnam. We have to prove that C connected. If it is not possible, if it is possible, C is not connected until continue this way. From 1 and 2, so from 1 and 2, so one equation. So E subset of C subset of E subset of E bar is the first equation. Second equation is E is equal to A union B. So A intersection B complement is equal to empty. A complement intersection B is equal to empty. So this is a second. From 1 and 2, we can see E subset of C, E subset of C. So C is equal to, what is the C is equal to? A union B can be written as, whenever E subset of A union B, E subset of A union B. Showing that E subset of A union B, then he is called is A comma B are two separated. E subset of A and B is contained, showing that is a connected set E contained in the union of two separate sets A and B. So separate sets A and B. Hence it is follows that either E subset of A or E subset of B. Now E subset of A union B, showing that the connected set E is contained in the union of two separated sets A and B. Hence it is follows that either E subset of A or E subset of B. So either. So that is, I'm taken the first case, I'm taken the second case. So what is the first case is E subset of, like this. This is E subset of the first case. E subset of A then implies that is E closed set is subset of A bar closed. So both side intersection B apply chandi. E bar intersection B subset of A bar intersection B. So this is E subset of A. This implies E bar subset of A bar. Both side intersection B apply chandi. E bar intersection B. Right side A bar intersection B. This is subset of empty. Then is equal to empty. So E bar intersection B, E bar intersection is equal to E bar intersection is equal to empty set. So your equation number 3. So equation number 3. Next is equation number 3. So from 1 and 3. So from 1 and 3 we got is next. So 1 and 3 in choosing C. C is subset of E bar 1 and C is equal to A union B. So A union B is a subset of E bar. So E bar. So therefore, every B subset of A union B, up to B subset of E bar, both side he intersection apply, B intersection B left side, right side E bar intersection, B subset of this is called is C subset of E bar. So C is equal to A union B. So A union B subset of E bar. Every A union B is contain B subset of E bar. So E bar, whatever E bar intersection B is equal to B. In the since, so B intersection B left side, right side E bar intersection B. So left side is equal to B. Therefore, E intersection B is equal to E bar intersection B is equal to B. This is the fourth equation. So from third and fourth, third equation, and else we know that third equation is, so third equation is E bar intersection B. So third E bar intersection B is equal to empty. This is called fourth equation. E bar intersection B is equal to B, and you can substitute pi is equal to B. B is equal to pi another, which is a contraction. A comma B and both are starting in two sets. A comma B are two non-empty sets, which is a contradiction because B is non-empty set. Why this in contradiction? C is not a connected set is wrong. C is not a connected set is wrong. 100% therefore C is connected. 100% is C. B is equal to empty, which is wrong. 100% is C is a not a connected is wrong. 100% C is connected. So C is connected. So this is also theorem important. Now, next in page number same 4.7.4 theorem, same page number 48. 48 theorem is, so we got. So this is a theorem. So what is the theorem? E subset R equal to R. E is connected. If and only if X is belongs to E, comma Y is belongs to E. So this is E is connected if and only if X belongs to E, Y belongs to E. So X is less than Z is less than Y. So this implies Z is belongs to E. Z belongs to E. So that is called is, we have to prove now. Once again, now this. Okay. No. So this proof is proof. Suppose E is connected set. I'm taking suppose E is connected. E is connected. E is connected. Also suppose X belongs to E, Y belongs to E, X is less than Z is less than Y. So we have to prove. We have to prove Z belongs to E. So if it possible, I'm taken Z does not belongs to E. Assumption, I'm to wrong sentence. So Z does not belongs to E. Assumption, that wrong sentence I'm taken. So this is called this. Okay. So this is assumption Z does not. A is equal to one interval. What is the A is equal to interval is minus infinity to Z. Intersection E. B is equal to one another interval. E intersection Z to infinite. Okay. So what is a open interval? This is minus infinity to plus infinity. Real line. We got, this is, we got. So minus infinity to Z. Z to infinite. This is a interval. So it is a, now it is a different intervals are there. A is a minus infinity to Z. And what is A is equal to minus infinity to Z intersection E. So B is equal to E intersection, so Z to infinite. Both are A intersection B is equal to no common element. There is no common element, is empty. Chudandi, this is a real line. So minus infinity to plus infinity. This is Z. So it is a, sorry. This is minus infinity to plus infinite. So is a open. So what is the, this is a take now. Z to Z. So there is no common element, is a intersection part. I am taken A union B. Is a taken A union B. What is a A union B? So minus infinity to Z intersection E. E is a union. Is a union. So union of, this is E intersection of Z of plus infinity. So this is in two intervals inverted. So what is the common is called this. So what is the intersection is common? Minus infinite to Z union Z to infinite. So this is the intersection E. Intersection E. So intersection E. So you can. So this is a real number line. And this is a real line minus singleton Z. So intersection E is equal to that is a E. So it is equal to E. So it is E. Thus gives now. So this gives. So this gives compulsory. But intersection just same a real number or a singleton Z. So intersection E in totally is equal to E osadi. It is a right side A union B. So this gives A union B is equal to E. This gives A union B is equal to E. This is a part. So this gives A union B is equal to E. This gives A union B is equal to E. What is a Z is a belongs to? So point X comma Y. Where is the X is a belongs to? A. What is the Y is a belongs to? B. So A and B are B non-empty sets, non-empty. So non-empty is a, so what now? Non-empty. So this is called as A complement intersection B is equal to empty. A intersection B complement is equal to empty. So A comma B are ఏమైతే are two separated set. Two separated set. So two separated set E is equal to A union B. E is equal to A union B, two separated sets. Then he is, this is E is equal to can be written as union of two separated sets. E can be written as union of two separated set. That he is called is not a disconnected, not a connected, not a connected. Other name is called is not a is called E is a disconnected. E is disconnected. Disconnected is mean which is a contradiction. మన assumption main sentence తెలుసు he is connected. నేను తీసుకున్నది wrong. Z belongs to he అనేది is wrong. 100% ఏమైతే చెప్పండి, x is less than z, z is less than y. So z is must be belongs to e. You have to prove. So x belongs to e, y belongs to e, x is less than z, y is less than. So is 100% z belongs to e. So this is a part. So it's a now again. Now this is a part is a conversely part. What is a conversely? This is a conversely. So suppose that x belongs to he, x belongs to he, comma y belongs to he. So y belongs to he, x is less than z is less than y, and z is belongs to he. This one we take. We have to prove. We have to prove that E is connected. We have to prove that E is connected. Suppose I'm to take an M. This one suppose he is disconnected. E is disconnected. Assumption. Then E is a disconnected. He can be expressed as two union of two separate set, A union B, two separated set. And what is A intersection B complement is equal to pi. A complement intersection B is equal to empty sets. So x is belongs to A and y is belongs to B, such that x is less than y. So x is less than. If follows we define the z is equal to supremum is least upper bound of A intersection of x comma y. A intersection of x comma y close is the equation 1. So x belongs to A. A intersection of x comma y is non-empty. Since A intersection of x comma y is contained in x comma y, these give A intersection x comma y is a bounded. Every least upper bound is bounded. We know suppose that. So we know suppose that E is subset or equal to R. So it is a non-empty, is a non-empty set of real numbers, which is a bounded above, which is he and which is bounded above. Y is equal to, it is a supremum of bounded about a supremum of E. So supremum of E. So this is called is a supremum of E. So Y belongs to he bar, where he bar is. So Y is belongs to he bar. Since E bar is a closed set, E is a closed. Z belongs to A bar. Since so Z belongs to A bar, I think. So A intersection B is equal to B complement. A bar intersection B is equal to complement. Z does not belongs to B. So Z does not belongs to B. So where x is less than or equal to z, x is less than or equal to z is less than y. This is a second equation. So this is called is in second equation. So we have to clear. So if we z belongs to A, if z belongs to A, then z belongs to A, we take first case, x is less than z is less than y. So therefore z does not belongs to A union B. Therefore z does not belongs to A and z does not belongs to B. I say z does not belongs to A union B. So called therefore z belongs to A. Z belongs to A in the first case. Then x is less than z belongs to A. So x is less than z is less than y. So therefore z does not belongs to A union B. So z does not belongs to E. So which is a contradiction. Therefore he is connected. E case lo he is connected. So we get to see the second case. What is the second case is called is? No. Now again second case is, the second case is it's a clearly no. So the second case is if Z belongs to A. So if Z belongs to, so Z belongs to A. So Z belongs to A. Z does not belongs to B bar. So B bar is equal to also B union B complement. Therefore, does not belongs to B union B complement. So Z does not belongs to B, and Z does not belongs to B complement. So B complement. So B complement. So then there exists interval, open interval. So what is a Z minus of epsilon, Z plus of epsilon in a real number system in real, which is does not contain a point of B. There exists a point Z1. So Z1 such that Z is less than Z1 is less than Y. So Z1 is does not belongs to B. So Z1 does not belongs to B. So it is the same thing. X is less than or equal to Z. Z is less than Z1 is less than Y. So Z1 is a does not belongs to also A. So Z1 does not belongs to, already we know that, to B. So Z1 does not belongs to A union B. So Z1 does not belongs to E is also. This is a contradiction. So already Z1 another kuda belongs to E, which is a contradiction to fact that. So what is the fact that is X is less than Z is less than Y. So Z is must be belongs to E. So it is our assumption, our supposition that E is a not connected is wrong. E is a disconnected is wrong. 100% he is a connected. E is a connected. So this is called this. So we have to last theorem is this is a theorem is got to 4.9.1. 4.9.1. So this is a 4.9.1. Subset of X. Subset of Y subset of X. Then E is a compact. Now, so this is a theorem is the last theorem. You can expand. Suppose E subset of Y subset of X, then he is compacted to related to X if and only E is compacted to related to Y. E be a compacted to related to X. To prove that E is a compacted to related to Y. So that is E compacted to related to X to definition every convergent G alpha. This is a G alpha. So is a open set in X. So for he, there is a finite subcover he in X. Finite subcover is taking. So what is a finite subcover is V alpha. This is a V alpha such that alpha belongs to I. So we have open cover in E in Y. So E is a open cover of E is subset of, so union of open cover of V alpha. Since E is a compact, compact column is containing is open, where V alpha is an open related to Y. There exists an open set G alpha in X such that V alpha is equal to, so G alpha intersection Y. So Y is equal to the Y intersection G alpha also. So therefore, so V alpha is equal to G alpha intersection Y. Therefore, so V alpha subset of G alpha. So both sides union apply. So therefore, this is a union of alpha. It is a, so union of alpha is a V alpha. Subset of union of alpha G alpha. The union of alpha E alpha is nothing but E. So E is a subset of union of alpha belongs to high is a G alpha. And he is a containing a G alpha. And G alpha is a open cover. G alpha is a open cover in X. G alpha is a open cover in X. E is a compact to related to X. E is a compact to related to X. Next is also conversely part, same part. So the same part is also he is a compact to related to X. We can find finite subcollection G alpha 1, G alpha 2, G alpha n from G alpha n. So such that E subset of G alpha 1 union G alpha 2 union. So G alpha union. So it is also G alpha union G alpha. So E subset of Y. So E subset of Y is the intersection G alpha 1 union G alpha 2 union G alpha n. Same intersection is common. So therefore E subset are V alpha 1 union V alpha 2 union. So V alpha 1 V alpha 2 a finite subcollections of E intersection. E is a compact related to Y. Is a conversely part also. So where it's a part is a conversely part in part of homework part. So this part is completed. Next is also homework. This is a 4.9.2 theorem. This is homework. So the topic is completed. Next is to be started is continuity and compactness, connectedness. So okay, all of you.
Thank you, sir.